I have a class from 9 until 9:50, and at about 9:10, I heard my dog. My dog was in her crate. I heard her. She's scratching, she's barking, and I was like, "Ah, puppies. Oh, puppies." And she kept doing it. And I was like, "I can't leave class. I can't leave my class." And she just kept going, kept barking and everything. And then I got up there because she stopped barking at about 9:40 and she had an upset stomach. And oof. So it's very appropriate that we're talking about gases because there are some intense odors that I just smelled. And I'm sorry if that's crude and crass. I apologize for that. But we're still going to talk about gases. I'm done talking about my dog's gastrointestinal distress. Instead, we're going to talk about gases. Now, if you remember the other day when we were talking about gases, we talked about a couple of different relationships between different things related to gases. We talked about pressure and volume, volume being the space that a gas occupies, and then pressure being basically the force that a gas is under, or that it is exerting. Um, so just as a quick rehash, we talked about the relationship between pressure and volume. You remember that if we increase the pressure, then the volume that a gas occupies goes down. Okay. Now, one thing that some of y'all might be good with this, but this is something I always have to kind of work around in my head is a mathematical relationship, direct and indirect. Um, and so here what we have is, and one way to kind of process calculations is, or process equations, is when you see something like this, P1 V1 equals P2 V2, I think that it's useful to then say, okay, well, if pressure and volume are on the same side, and then they're on the same side, like they're being multiplied by one another, that means if one of them goes up, the other one goes down. That's one way to kind of look at this. Now, if we then, so when we see an equation that is P times V equals P times V, those things are being multiplied by one another. If one goes up, the other has to go down. Now, looking at this equation, V over T and V over T. Well, if volume goes up, what do you think happens to temperature? Since it's not multiplication, that's probably going to go up as well. If volume goes down, then temperature is probably going to go down. Now, we did a calculation with this the other day, but the last thing that I want to say before we proceed is the relationship between volume and temperature. That's Charles's law. Now, what we're going to look at today, we're going to name a couple of the other laws because close that. Um, because it's kind of helpful to look at them and know their names. But ultimately, what we're concerned with, and maybe not concerned, but what we're interested in is the amount of a gas, the volume of a gas, the temperature of a gas, and the pressure that that gas is under. Now, here we go. Let's see. I gotta make this full screen. I'm gonna switcheroo, dunzo. Man, sometimes I hear myself speak and I'm like, Joel, you say a lot of silly words. Dunzo, you don't have to say that. Switcheroo, also don't have to say that. That's not real words. At any rate, relationships, gases, gas laws. We talked about pressure and volume the other day. Then we talked about volume and temperature. Now we're going to talk about pressure and temperature and volume and amount. Now, with this in mind, all of these gases and all of these laws related to gases are going to be combined into one. And that combined law is commonly known as the combined gas law or the ideal gas law. So we'll get to that, but I think that it's helpful to kind of think about these all individually and kind of build it up into something collective or like collect it all into one big thing. Now, our relationship between pressure and temperature is depicted like this. Pressure is equal to constant times temperature, which is very similar to what we saw when we looked at volume and temperature. Now, what do you think will happen to the pressure when we increase the temperature, but we keep a constant volume? So is it going to increase, decrease, or not change? I think what we're going to do is look at an example. Let's just go ahead and let's watch this little video here. Oh, darn it, did I? Okay. Oh, good, good, good. Now I got to switch my share though. Okay. Boop, 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 boop. Okay. Here is pressure, temperature, gas law. Okay, so what we've got is we've got a cube, a nice cube that we've got a bunch of little molecules representing gas molecules. On the right-hand side, we've got pressure, volume, and temperature. P, pressure, T, temperature, V, volume. Now, before we proceed, add to the chat, what are the units for temperature? Kelvin, perfect. Well done. Um, so our temperature, anytime we talk about gas laws, we always want to put it in Kelvin. How do we get from, let's say it's 6 degrees Celsius outside. What is the temperature in Kelvin? 6 Celsius. Caitlin's on top of it. 273.15 plus 6 or 279.15. Well done. I feel like Caitlin was kind of putting that out there like, can you do this? Can you add this up, Joel? I can. Did it. 279.15. Perfect. Okay. So that's our temperature in Kelvin if it is 6 degrees Celsius. Now, here what we're going to do. Thank you. Thank you very much, Caitlin. I appreciate that. After cleaning up my dog's mess, I really needed a good job because the dog certainly isn't going to say it. But again, I'm done talking about my dog's gastrointestinal distress or its upset stomach. Thank you. Okay, here we go. What we've got is our closed container and we got gas molecules in there. We watch our dials. What are we going to see? We're going to see changes in any of those dials. Okay. Now we're going to put pressure. Okay. So think about this as, or sorry, what we're going to do is reduce the temperature because here, what this is showing on the left and top, those are ice blocks. So those ice blocks are going to cool this system down. What's happening to the volume? Nothing. What's happening to the pressure? It's a pressure drop, which I think is a song. Pressure. It's like a ska reggae song from the 70s, 80s. The Clash did it. Everyone had to do that one. Okay, so we see the pressure drop off because the temperature is going down. Huh? Well, you're cooling it down. Effectively, what you're doing is you're taking energy from that system. You know, I've used the 4-year-old's preschool class as an example. If you drop the temperature in a 4-year-old's classroom, of course, safely, we're talking like 60 degrees. We're not talking like negative 200 degrees. We're going to bring the temperature down, and all those little kids are moving around. As the temperature drops, what are they going to do? One, they're probably going to start screaming and yelling because that's just kind of what they do. But then it's going to get colder. Their movement is going to go way down. Not like hazardly low, but instead just kind of like, I don't want to move anymore. I'm cold, which is what my kids do. Whenever it gets cold outside, they walk outside and they say, it's freezing, and they stop moving altogether. I would argue, hey, just keep moving and then you're going to warm your body up, but never mind. Okay, so all of these molecules, as the temperature drops, the pressure drops because all of those molecules are going to stop moving. Now, the other day when we were talking about and looking at a similar system like this, all of these individual molecules we saw whenever the temperature was high, these little blue balls, what were they doing in terms of, I'll say, bumping into things? Were they doing it more? Were they doing it less? Were they doing it at all as the temperature was high? Good morning, Aurelio. Yeah, they're collisions. The number of collisions that those molecules were having with the walls and with each other was super high when the temperature was high. Okay. And when we saw that, when the temperature went up, well, then the number of collisions went up. When the volume went down, the number of collisions went up. When the number of collisions goes down, what that means is that the number of collisions that they have, or sorry, when the number of collisions goes down, then they're not hitting the walls. They're not kind of exerting force outward. So the pressure is going down. So there's a relationship between frequency of collisions and pressure. There's also a relationship between frequency of collisions and temperature. But for looking at this, when the number of collisions, or sorry, when the temperature goes down, so does the number of collisions. And the number of collisions is basically on par with the pressure. Okay, so now let's go ahead and do a quick calculation. And for what this looks like, let's say that I'm going to go ahead and define pressure in terms of atmospheres. If you remember, the units that we have for pressure are atmospheres. And let's say that this is 1.5 ATM. Now, I did go to school at Texas A&M, but this ATM has nothing to do with this. Instead, these are the units for atmospheres, or the units for pressure. ATM here equals atmospheres. Okay, now let's imagine that before the ice was added, I'm going to scribble the ice out here. Okay, before the ice was added, our initial temperature, let's say that it was 355 Kelvin. Okay, cool. Then we added the ice. Give me a new temperature. And since it's a Kelvin scale, can it be negative? Add to the chat. Can it be negative? No, you're absolutely right. I tried to freeze my face like that to see if anyone was like, did he get disconnected? But instead, I was just sitting still. Okay, so now somebody give me a new temperature. What did the temperature drop to? Good, I got you, Amira. Great. What's our new temperature? Give me a new one. It can't be negative. How about let's just go to 305. We'll keep it conservative, a minor change. Okay, so here's our new temperature, 305 Kelvin. We're going from 355 to 305. Okay, now what we want to do is calculate the pressure. Our temperature dropped. We're kind of expecting our pressure to drop, and that's kind of what we saw with this dial right here, because our volume remained the absolute same. Okay, so what I'm going to do is I'm going to use my calculator and I'm going to plug in. Well, first I got to press the Windows key to get calculator. Then I'm going to do 1.5 divided by 355. Okay, that gives me a super small number. That is zero. Oh, stop right there, Joel. 0 point calculator. 0042. We'll go 0042 to 54. Okay, there's that. That is what I get when I take 1.5 and divide it by 355. Great. Okay, so now I have 0.004225. And where did these numbers come from? I made them up. P2 over 305. Okay, so now I'll multiply each side by 305 because that 305 is in the denominator. And when I multiply each side by 305, then gets rid of it here. And now I got to put this in parentheses to say multiplied by 305 Done. So now 0.0042254 times 305 and our pressure. Ba-ba-da-ba, ba-ba-ba-ba-ba-ba, 1.289. What are our units for pressure? Atmospheres. Perfect. Great job, everyone. So our units for pressure are atmospheres, ATM. Okay, so I've got that. So what we expected based on the number of collisions, or kind of imagining the number of collisions, we expected our pressure to drop. Mathematically, did our pressure drop? Essentially, is 1.5 larger than 1.289? Absolutely. So our pressure did drop. So that's what we expected to see. That's great. Now, why is that? Well, because we maintained the same volume. Our volume stayed it stayed constant. If our volume had changed, well, then we're introducing a different, what's called variable. And so then would our pressure have dropped? Maybe. It's really kind of hard to tell. But this equation, what we're looking at strictly is a relationship between pressure and temperature. So now I'm going to jog back. What do you think will happen to the pressure when we increase the temperature at constant volume? What do you think is going to happen to our temperature? Increase, decrease, not change. A is increase, B is decrease, and C is not change. Add to the chat what you think that is based on, the calculation we just did. A, it increases. Spot on. Great job. Increase, yes. Okay, so keep that in mind. What we're doing is we're piecing all of these different things together so that eventually we're going to be able to look at something like this, and I'm going to say, hey, the temperature decreases, but the temperature decreases, but the volume increases. What happens to the pressure? So we'll be able to introduce two variables and two changes and piece it back together. Okay, now next up, our last of our four independent gas laws, the relationship between volume and amount. Now, amount is like, if I've got a bunch of thumbtacks here. As I've said before, I have ADHD, so I've got a bunch of stuff on my desk. Got thumbtacks, I've got a little screwdriver for fixing glasses or watches. I don't wear glasses, but I still have this here just in case. Here, I'm counting my thumbtacks. I've got 5 of them. Okay, 5 thumbtacks. That's a unit. Thumbtacks would be a unit. I could also look at that and say, put it on a digital balance and say, oh, well, I have, 205 grams of thumbtacks. Also an amount. Now, here, and before I actually switch slides here, could somebody add to the chat what unit we use in chemistry? Maybe you've taken a chemistry class before. I think maybe I don't know that I've mentioned this unit before. Maybe I have. Yeah, I think I have early on. What unit do we as chemists use? I'll give you a hint. Starts with an M, and a few days ago, yes, great job, cortisone, moles. Now, with that in mind, 1 week ago today, people celebrated Mole Day, International Mole Day. 10/23, October 23rd is Mole Day because, well, the number for a mole is 6.02 times 10 to the 23rd. Now, we're going to get more into moles later on, but a mole is a quantity like a dozen. 1 mole of blank equals 6.02 times 10 to the 23rd blank. So I always like to think about dollar bills. If I had 1 mole of dollar bills, I would have 6.02 times 10 to the 23rd dollar bills. Now, here we are talking about volume and amount. So keep that in mind. Amount, we're talking about moles. And we depict amount using the single lowercase letter n. N is moles for our unit. Now listen to this. What do you think will happen to the volume when we decrease the amount of a gas or decrease amount of gas particles in at a constant pressure? Okay, now think about this. The other day, I was telling you about, oh, you got this Dr. Pepper bottle. And in that Dr. Pepper bottle, here's a Dr. Pepper bottle. We've got our nice label, Dr. Pepper. Okay. I don't work in marketing or um, drawing, but that's a pretty good Dr. Pepper bottle. I think that I'm kind of dynamic when it comes to my skill set. So here's our Dr. Pepper. Scribble, scribble, scribble. I asked you a question the other day. I said, what's above the Dr. Pepper between the top, the cap, and the Dr. Pepper itself? And the question that, or the response that I got, thank you, Gabriel. Thank you. It's true. The response that I got was, well, I think that it's probably some CO2, carbon dioxide, and O2. And I think most everyone's like, oh, yeah, I know that it's carbon dioxide because, whenever I shake up a Dr. Pepper bottle and then I open it, well, then it sprays everywhere because a Dr. Pepper is a carbonated beverage. And you want it to be carbonated because if it's not carbonated, ugh, there's a flat Dr. Pepper, really unpleasant. There are definitely like worse things in life and everything like that, obviously, but a flat Dr. Pepper is not something that anyone's really excited about. When you get one at like a gas station at the fountain, you're like, I don't even want to pay for this now. But you do because you're honest, you have integrity, and you don't steal. So we've got carbon dioxide and O2. Now let's imagine that Dr. Pepper bottle is under pressure, under a certain amount of pressure. That's why, like, when you push on the side of it, it doesn't like collapse inward. But let's imagine this space, and let's say that, just for the sake of kind of the example, let's say that we've got 5 CO2 molecules and 5 O2 molecules. So there's a total of 10 molecules in there. Now, if you were able to, let's say that you got a really, really fine needle and you were able to put the needle into that Dr. Pepper bottle. And then this is a syringe. And yeah, that's a syringe. That's a good one. And then of course the syringe has a plunger. And let's say that you were able to basically suck out all the CO2. We've gone from having 10 gas molecules. We've removed all the CO2. Okay, so instead of 10 molecules, we've got 5 gas molecules. Does anyone disagree with that? And let me go back. This is our magic super fine needle that basically finds its way into that plastic without allowing anything in, and you just remove that CO2. We've got 5 gas molecules. I think everyone's in agreement there. Nobody said anything saying no, 10 minus 5 is 9. Instead, everyone sitting, yeah, I get it. I'm down. Okay, now, with those 5 gas molecules that are left, let me ask you this. When we've removed 5 molecules, half of the gas in this space right here, let me change colors because I really want to punctuate and accentuate this. In this space right here, that previously was just CO2 and O2, but now we've removed the CO2. Is that space the exact same size? That's my question for you. When you remove half of the gases, is that space that holds the gases the same? No, perfect. Cortisone, you're absolutely right. Okay. Now, another way to kind of visualize this is, like I said, I've got a lot of stuff on my desk. I've got name tags. I've got my student ID from when I was a student at Blinn College. I'm going to need this. I don't know when I'm going to need this, but I'm going to need it. And look at that guy right there. Yeah. I had, I decided that I wanted to, I don't know, look tough on my student ID picture at any rate. So I have all those IDs, and I bring that up because I'm going to give you a little bit of a demonstration. So here, what I've got is Ziploc bag. That's what all my IDs were in. Ziploc bag. And here's this. Let me blow it up a little bit more. Okay, so here's my Ziploc bag. It has a certain amount of gas in it. Now I'm going to remove some gas from that. What happened to the size, the volume of this Ziploc bag? Whenever I removed some gas, what happened to the volume? Did it get larger or did it get smaller? Well, I'll tell you, it got smaller. Absolutely right, Cortisone. It got smaller. The volume decreased. So when the amount of gas decreases, so too does the volume. Now, with that in mind, let's go ahead and look at the mathematical relationship and an example of that. Here, what we have is somebody blowing up a balloon. What are they adding to that? Chances are they're adding more gas to that balloon. And when they add more gas to that balloon, what happens to the volume of it? It increases. Now, with that in mind, I brought up moles. I brought up the unit of a mole. And that's important because when you do a calculation with this equation right here, this N value, N is number of moles. Now, with that in mind, let's say that we have let's say that oh, rats, what just happened there? Ah, ah, Joel, stop pressing buttons. We've got let's say a container, and we're just going to do the math to show this. What happens to the volume when we double the amount of gas at constant pressure? Is pressure in this equation at all? Nope, because it's kept constant. So now let's say that we have an initial volume of 1.2 units for this. Best units are going to be liters. And then let's say that we have 0.8 moles of a gas. And we're going to set that equal to the equation where we are trying to figure out the volume. We don't know what our volume is, but we're going to double the amount of our gas. We're going to double it to 1.6 moles. So 0.8 times 2 is 1.6. So we've gone from 0.8 moles of gas to 1.6 moles of gas. What happens to the volume? I did my best to kind of crack my voice like I was a teenager again. But what happens to our volume? Well, what we can do is we can say with our calculator, 1.2 divided by 0.8, that's going to be 1.5. 1.5 times 1.6 goes to... So does everyone follow what I did there with the math? Let me actually rewrite this and give myself a little bit more space. 1.2 liters. This is, again, just the volume that I put together in my head. 0.8 moles gas is equal to V2 over 1.6 moles of gas. So 1.2 divided by 1.2 divided by 0.8 is 1.5. That is equal to V2 over 1.6 moles of gas. Multiply each side by 1.6. Done, done. 1.6. And that gives us our V2, which our V2 is equal to 2.4. What are our units for this? Units for volume. I know the first person who's, I was going to say, I know the first person who says in the chat is going to get it right. And Kaylee, you're absolutely right. 2.4 liters. Okay, so we got 2.4 liters. What happened to our volume? It doubled. We doubled our amount, we double our volume. Those two things are directly related to one another. Now, before I call it a day on this stuff, and this was intended to be my like bookmark end, we've talked about 4 different gas laws and 4 different relationships here. Pressure and volume, volume and temperature, pressure and temperature, volume and amount. There are a couple of things to keep in mind with this. When you're talking about the relationship of pressure and temperature, and when you have that relationship, the amount of the gas and the temperature cannot change and do not change. The volume and temperature, when you're talking about that relationship, well, the amount of the gas and the pressure of the gas do not change. So basically, when we're looking at a relationship between these 2 variables, then the other 2 variables remain unchanged. If we look at, for example, volume and amount, well, this would be a totally different question if we said, oh, but the temperature goes up 15 degrees and the pressure goes up 2 units. So you can't change those things. Okay. Now, the very, very, very last thing that I wanted to say before I tell you to have a wonderful day is, let me ask you this, and I need responses in the chat on this one. I said 0.8 moles of gas. Now my question in the chat, or one of my last questions, my question in the chat right now is, what gas? Like if we're looking at this right here, somebody blowing up a balloon. Mostly that's going to be carbon dioxide because that's what we exhale and that's what plants get from us. But what gas am I mentioning or referencing here with the 0.8 and 1.6? And, you know, CO2, O2, I don't know. Hydrogen gas could work. What I'm getting at here with this is, did I identify a gas? Did I say 0.8 moles of CO2 gas? I didn't. I just said 0.8 moles of gas. And then I said 1.6 moles of gas. I didn't change the amount, or I didn't change the identity. In fact, I didn't even mention the identity of the gas. Why do you think that is? Why did I not mention the identity of the gas? I didn't. Caitlin, perfect, perfect. The identity of the gas does not matter. Corazon, you're absolutely right. It's constant. But if I were to present this problem and I were to say hydrogen gas, H2 gas, or CO2 gas, does that change the calculation at all? Nope. If it's CO2, if it's H2, if it's water vapor, if it's nitrogen gas, it does not matter. So when we are talking about gas laws and relationships that gases have with or amounts and volumes and temperatures and pressures, the identity of the gas, and I'm going to write this all very over the top, over the top and dramatic, and maybe unnecessarily dramatic, does not matter. Almost wrote Mattel, but it does not matter. The identity of the gas does not matter. If it's CO2, if it's H2O, if it's H2O2, it does not matter because all of these gases are largely going to behave the exact same way. If you add more O2, what happens to the volume? Goes up. If you add more H2, volume goes up. If you decrease the amount of CO2, the volume goes down. So this is an instance where you don't need to worry about the identity, but one thing that you do need to be kind of thoughtful of is the unit. So our unit for N is moles. Now, we're not quite here at this point, but if basically if I said you have 26 grams of H2 gas, well, first of all, does a gas have a mass? Absolutely. You know, if you have a birthday party and you get a helium gas tank, yeah, you can't really lift that up super easily. It's heavy. The tank is heavy, but also there's compressed gas in there. So gases have mass. There's no doubt about that. The identity of the gas the unit here, if I gave you 26 grams of gas and then you add 15 grams of H2, well, that's a calculation that we're not really ready to do because of the fact that the amount of our gas is listed in grams as opposed to moles. In order to do this calculation, we have to have units of moles or units of our gas in moles. Okay, that's where I'm going to stop. Now, I'm going to stop my recording